Hi, everybody. Scott Cart here with a special request from one of my subscribers. They asked me to take a look at a LM2576 buck regulator and to basically walk them through how to create this design. I'm sorry that it's taken this long to get caught up to some of the videos that I needed to make, but as promised, here we are. Okay, so the first thing that I really want to talk to you about is this is not a new chip. This is been around for quite some time. It only runs at 52 kilohertz. So its switching efficiency, they say, is about 75%. So it's not great, but it is a lot better than a linear regulator. And as you can see here, this came out in August of 2005. So we're talking about almost 2 decades ago. Very old chip. And now specifically, they asked me to look at the 5 volt. So we don't have the voltage divider over here, but if you're interested in seeing how that voltage divider works, the formula is almost identical to the LM317, which I will link in how to do the calculation for that. Now, the rest of the circuit, basically what we need to do is follow the design application note here. So we have our power coming in, and we can see that we have 4 to 70 volts is what they're calling here. And the reason for the 7 we'll take a look at in a second, but it's basically needs a minimum of 2 volts across here because of the FET in order to switch on and off. We have a ground pin, obviously, and we have an enable. Okay, so this is active low. So as long as we pull this low, it should run. We have an output. So this is basically going to be sourcing power into the coil, and then when we release the coil, the energy is fed back through the Schottky diode here, and basically bucks the voltage down. And then we have a feedback on both of them that will tell the comparator inside how it's doing and whether it needs to increase or decrease the duty cycle. Okay, so I guess the first thing that we need to talk about in all of this is the best way to learn how to apply a chip is to read the data sheet. Okay, and so here we're reading the data sheet, and some very simple parameters as to the pinout, which is fantastic. And then we get down into the operating specifications and all the normal stuff that you expect to see. So our voltage out for the feedback, what have you. And we can scroll through most of this. It doesn't have a whole lot of effect. You will see that V in minus V out will be in here somewhere, and it'll be about 2 volts. And the thing that's kind of interesting that I couldn't find is a calculation on what the inductor should be. And so that's kind of a curiosity, but we do have a couple freebies that they give us here. One of them is this typical application here. And so my suggestion is to basically just follow this, and we can always tweak it and go from there. Now, the inductor itself, we do need to be a little bit careful to not exceed too much one way or another. If the inductor is too small, the current carrying capacity won't be there. But if it's too big, the duty cycle will get skewed, and you're going to have trouble. There's a couple more things that we can talk about here with this image, and one of them, and my students should recognize this. These are called star points, and so this is telling us when we do our layout that we want to be really careful to make sure that these points are as close as possible. Okay, so we'll grab our Proteus here. We'll try to pull in our part. And so we're looking to bring in a LM2575-5.0. And you'll notice that there isn't anything in Proteus, but we do find something with our Schematic and as well as Snap EDA. And so I'm already signed up for this one. So here we go. And perfect. WU. It's a surface mount package. So I'm okay with the surface mount myself. So I'm going to pull that in. Yes, I'd like to import it. Okay. And why don't we grab some more parts while we're here? So we're definitely going to need an inductor. And so I'm going to use real inductor. Sure, we'll grab that one. I like the real inductor because it allows me to play with some stuff when it comes to simulation. We're also going to need a capacitor. And I like this symbol for my capacitor for non-polarized. And we'll grab that guy for polarized. Electrolytic. And that should be it for components. And so again, just following what's in the data sheet, we're going to go ahead and drop in our part. Okay, I'll rotate you around. And we'll start bringing in some parts. We've got 100 microfarad capacitor here on our in. Something that's not specified that we're going to want is a bypass capacitor. So we'll toss one in here. And I forgot to grab our Schottky diode. Okay, so in essence, we've replicated our circuit, and that's pretty much all there is to the schematic. Now, we'd obviously want to start changing some parts around to better accommodate our footprints. For example, we could go in and start changing these packages around to something surface mount, because if we're going to do surface mount, why not? Yeah, that looks more like it. That's going to be the sort of thing that we need for that guy. Perfect, and it's going to complain. So let's go in and we'll fix this. So we have our anode and our cathode. And so our cathode here is obviously going to be this. And our anode, we want to connect this and this. Come on. Okay, so here's our schematic. Good enough for now. It's quite crude, I get that, but let's jump into doing a little bit of board layout with it. Okay, so the first thing is we're going to assign a couple footprints. I assigned just random parts to this, so please don't think that this is the end all and be all. The idea here is to just show a couple quick things about how to do a layout like this. And again, keeping in mind that we want to keep these power nodes and the ground nodes as tight as possible. We really need to think about how the current is going to be flowing through this. And the longer it is, the more radiation it's going to emit. And so when we put in our diode, we want to have it in as clean a position as possible to not cause any real transmission issues. Okay. So let's And you'll notice on some of the chips, they actually give some hints, we'll call it, for layouts. This chip doesn't have it, and that's okay. We can deal with that. All right, we'll throw a board edge on this, like so. And again, this is all completely random. There's nothing too awfully special about what I'm doing here. We'll put that on the top. We'll make sure that we have a nice heavy trace here. Because again, we're looking for as little resistance to flow as possible, right? All right. Well, I'm happy with that. Couple things that we could change. Obviously, this is single-sided circuit board right now. You know, I'd flip these capacitors around to the other side if I was actually going to use single-sided. We can definitely change the relief on this. Something a little bit heavier would help. Let's see, boundary. There we go. We'll set you both to 25. So this will give us a little bit more current carrying capacity through here. Because we would be worried about heat dissipation at a maximum 75% efficiency, we're going to be dropping quite a bit of energy through here. So you may want to actually use a double-sided circuit board and stipple this so that you had maximum amount of copper to transfer the heat to the other side. If you would like to see a video on that, I just created one on creating tented vias. Same sort of idea, but you can stipple this to increase your heat dissipation. And a fairly clean path. I'm happy with this as far as the layout. We didn't bring in the 3D model for that diode. It's the wrong package, obviously, for the capacitors and the inductor. But you know, for our purposes today, this is fantastic. The takeaway here is that if you want to learn how to lay out a chip or use a chip in your design, the answer is you need to read the data sheet. Okay, there's a lot of information tucked away in that data sheet, and you just need to go through it bit by bit. Unfortunately, we can't simulate this. This chip doesn't have a simulation model, and we could see if we could find the SPICE file, or we could try to build one up ourselves. But at the end of the day, it's not really worth it for something this simple. Now, that said, this is an old chip. This is 17 years old now, minimum. The technology is well over 20 years. I'll guarantee that. And it's expensive, not only for the chip, but for this very large inductor and very large Schottky diode. And one of the things that we really need to think about when we're creating a design is how much money and space are we willing to put into this design. And so my recommendation would be, you know, this is a great little jelly bean part, but there are better chips out there. Now, you know, if you increase from this is running about 25 kilohertz. If you bump that up to 75 or even 100 or 400 kilohertz, that inductor gets a lot smaller. Your switching diode, though, needs to become a lot faster. But you know, we've got this huge trade-off. Now, one of the downsides also is that you become more noisy. So lower switching tends to emit less radiation than high speed switching, which brings in some design considerations as well. But great. That's all I have for you on this topic today. Very specific to the 2575, but also some concepts for doing board layout. Okay, I hope this was helpful. If it was, please give it a thumbs up. If not, your constructive criticism is absolutely appreciated. A comment down below. And if you'd like to help support my channel, please like and subscribe. It helps me out to get more information out to other people, because that's the way the algorithm works. And I appreciate your time. All right. Thanks, everybody. Have yourself a great day. Bye now.